And I want to emphasize that this is joint with a heavy emphasis on my collaborator here, Stefano Moretta, who is a PhD student who is in his final year and currently applying for jobs. So if you're interested in this and you know of some possible postdoctoral employment for him, then please go ahead and talk to him. So this talk is going to be very much a kind of sequel to the talk that Alex gave yesterday. So hopefully you were paying attention yesterday when Alex defined what tropical differential equations are. If you aren't, if you didn't pay attention, don't worry, I'll review it quickly, but I'm not going to spend a lot of time because I want to I want to build on what Alex did and talk about some new things. So I want to quickly review Grigoriev's setup for tropical differential equations and tropicalizing ordinary differential equations in terms of semirings. So this was in Alex's talk, and I'll just review it here. So we start with the ring of formal power series over some field K. And for shorthand, I'm going to call this R. So this is my ring that we're going to be working over. And now we have the t-adic valuation, which goes down to the natural numbers union infinity. And we're viewing this as an idempotent semiring with the min plus structure on it. And for shorthand, I'm going to refer to this as T for the moment, T for kind of a tropical. And then there's this much of the picture is something that might be familiar if you've done non-differential tropical geometry. And then in the differential case, we add this new layer up above where we have this semiring of Boolean formal power series. So remember, B was the semiring with two elements, 0 and 1. And the condition was 1 plus 1 is equal to 1, and you can probably figure out the rest. So this map down here, I'm going to call it V, and this is the t-adic valuation. And I'm going to call this map W up here. And then there's an arrow that fits in here, which is also basically the t-adic valuation, but defined on Boolean power series instead of power series over a field. I'm going to call this pi, and this is, again, just the t-adic valuation. Now, V is a valuation, so it's multiplicative and sub-additive. It's not quite an additive map. It's not a homomorphism. But because we're defining pi on an idempotent semiring up here and mapping to an idempotent semiring, in this case, going vertically, the t-adic valuation actually turns out to be a homomorphism. It's a homomorphism of semirings. Now, over here we had a differential, which was d by dt. And over here, we had a differential, which you can think of as d by dt, or you can think of it as simply shift left. And the W map intertwines these, it commutes with the differentials. So D composed with W is W composed with D. Now, this map W is kind of like evaluation in some ways, but kind of not as nice. While V is multiplicative, W is not in general multiplicative. And I think Alex was calling this the support map. So it's not quite a multiplicative map. It's the idea of this triangle here is that we're going to be looking at, well, the W is like a valuation, but only when you push down to here. Now, one thing I want to emphasize is that down here, there's no differential. And up here, we do have this shift left differential. And pi is a homomorphism of semirings, but is a kind of, it completely forgets about the differential up here. Now, the differential up here satisfies this nice Leibniz property. D of AB is equal to D of A times B plus A times dB. And we're going to come back to this and modify it a little bit later on. So the point is, upstairs in this new layer that we're adding in the differential world, we have a differential, and downstairs we don't. Now, let's suppose that I have a differential ideal in this RIT algebra. So this is the algebra where the coefficients are in R, and R, remember, is my formal power series in T. And I'm looking at polynomials in the formal variables x1 through xn and their formal derivatives. So you can think of this as an ordinary polynomial algebra in x1 and x1 prime and x1 double prime and x2 and x2 prime and x2 double prime and so on, arbitrary derivatives of x1 through xn. So if we have a differential ideal in this differential ring here, then I can tropicalize it. We've got two choices. We can either use the W map or the V map. And the right answer is, Grigoriev says, we should tropicalize equations, tropicalize elements of a differential ideal by taking the lower map. So we're going to tropicalize with V and map down to, this is where my shorthand notation T comes in handy, something which I will write as T curly braces x1 through xn. Now this thing here, I've written it to look like a RIT algebra. And as an algebra over T, and T, remember now, is this idempotent semiring. As an algebra over T, this is the same as the RIT algebra. It's polynomials in these variables x1 through xn and their derivatives, but there's no differential here. So we don't have any differential on this semiring, but that's okay because we don't need to differentiate our equations. We only need to differentiate the functions that we plug in to the equations to check if they're solutions or not. So the tropicalization of my equations is basically it's the image of I under this coefficient-wise V map. So this is V applied coefficient-wise. And the tropicalization of my differential ideal lives in here. So this is how I tropicalize equations. I apply V coefficient-wise. Now the solution set to a system of differential equations lives in R to the n. So this is a power series for x1, a power series for x2, a power series for x3, and so on, such that when I plug them into each differential polynomial in I get 0. And when I tropicalize this, I take the upwards map. So this is W applied component by component. And so this takes me to, oh, I should have said my shorthand was this, I'm going to call S. So this takes me to n tuples of Boolean power series. And the tropicalization of the solution set of this differential ideal is something which lives in there. So equations, I'm applying V to the coefficients. Solutions, I'm applying W to the components. So there's this kind of balance between the two. Why do we do it in this funny way? Well, as Alex said, it takes a little while to get your head around this. But the idea is, if I have some polynomial f living down here, oh, and sorry, this should have been an s to the n. So if I have a differential polynomial with coefficients in this semi-ring T, where I don't have a differential, and I have an n tuple of Boolean power series, I can take this P and plug it into F. So the basic idea is, if I have X, my ith variable, and I have the jth derivative of it, I'm going to evaluate this on P by taking the ith component of P, which is a formal Boolean power series. I'm going to do the jth derivative of that, which means shift it to the left j times. And then I'm going to use this map pi, which takes me down into T, to get an element of T. So I can evaluate each variable, and I can then extend this to monomials in the variables xi. So I can evaluate f of P, and this gives me an element of T. And in fact, it gives me an element of T by giving me this element as a sum of a bunch of elements of T, one for each monomial term in F. And that's going to be important in a minute. So let's come back to Grigoriev here. Grigoriev says we start with R, which is our formal power series. We've got the support map going up here to S, and we've got V going down here to T. V is the valuation. It's the T-adic valuation. And we can, if we're given a system of ordinary differential equations over R, I can tropicalize it. The equations end up as tropical equations over T. The solutions are elements in S to the N. And we can check to see if a solution, if a point P is a solution by evaluating here. So if, actually, I think I've got this on a slide later on, so let me hold off on that. Okay, so I'm going to say in a minute what I mean by a tropical solution, but Alex has already said that. So the problem now is, what do we do if we're interested in studying p-adic differential equations? Well, the first step is we need to change R. So we're going to change R from from formal power series over this field K, which we're thinking of as maybe being a trivially valued field. And the support map was applying the trivial valuation to the coefficients of a formal power series. We're going to replace the K with something like the p-adic numbers, which no longer has a trivial valuation, of course. Or maybe you want to work with something a little bit more interesting, like the Tate algebra living inside there. So that means changing R. So now we've got this sort of a starting point. And the question is, what do we put over here? What's my new S and my new T? Well, if you're interested in getting any sort of information about differential equations over this guy, or over the Tate algebra, then you need to record not just which powers of T appear, but what are the p-adic norms or the p-adic valuations of the coefficients. So in fact, you probably want to map, you want to change what we use as the valuation and map down to, I'll write this as R2 with the Lex ordering. I'll add in a point at infinity for good measure and give this the min plus idempotent semi-ring structure. And this map, my new V here, is going to be defined by taking a power series. Well, let's say I have a power series A n t to the n plus higher order terms. And I'm going to send this to the pair where I put the n in the first component, and I'm going to put the valuation, the p-adic valuation of the coefficient in the second component. And so this gives me a point of R2, which I interpret as a totally ordered abelian group with the Lex ordering, and then I turn it into an idempotent semi-ring by adding the point infinity. Okay, so that's my V. What about my W? Well, an obvious guess would be you could take something like this T here is R with the usual tropical semi-ring structure. So that this is the tropical T rather than torus T. We could take tropical formal power series, and this W is going to be just applying the p-adic valuation coefficient by coefficient. And my map pi here is going to be, you look at the leading term, and into the first component, you put the exponent of the leading term, and into the second component, you put the coefficient of the leading term. So this would be, if I have a power series Bn t to the n plus higher powers of t, this is going to map to n comma b. Okay, now we have a differential here, which is d by dt. Here on the bottom, there's no differential. This map pi is a homomorphism. And up here, do we have a differential? Well, there is a differential. You can take a kind of tropical version of d by dt. And I'm just going to write down what it has to do. This differential that we put here, in order to make W intertwine the two differentials, is defined by saying d of t to the n is equal to, we're going to do the valuation of n times t to the n minus 1. So it kind of looks like the tropicalization of the differential on my p-adic formal power series. Okay, now W intertwines the two differentials. So D composed with W equals W composed with D. That's good. But what's a little bit unsettling is that this thing we have here with this particular differential, and it has to satisfy this rule if W is going to intertwine the two differentials. The problem is this differential that we've written down is no longer satisfying the Leibniz rule. So D of AB is no longer always equal to D of A times B plus A dB. So what do we make of that? Well, it turns out that even though this is not true, a weaker version is satisfied. Something that I'll call the tropical Leibniz rule, which is that if you look at D of AB plus dA times B plus A times dB, then this tropically vanishes. So equals the sum of any two of the terms, dA times B plus A dB. So I can drop the first term without changing the value of the sum, equals dAB plus dA times B. I can drop the third one, or I can drop the middle one, dAB plus A dB. So to say a sum of terms tropically vanishes is to say you can leave out any one of the three terms in it, or however many terms it has. You can leave out any one term without changing the value. And this is what we call tropically vanishing or satisfying the bend relations. And these bend relations come up a lot in studying the semi-ring algebra underlying tropical geometry. These bend relations are the correct generalization of the usual min attained at least twice condition when you are working in a semi-ring which is not totally ordered. If it's totally ordered, then saying you can drop out any one term without changing the value is simply saying the minimum occurs at least twice. If it occurs only once, then when you drop out the minimum term, you will change the value. But if the minimum is always occurring in at least 2 places, then dropping any one of them doesn't change the value because the min is also redundantly occurring somewhere else. Okay, so now I want to look at an abstraction of this setup up here. So the abstraction is going to be, we're going to have a differential ring, R. I'm going to have a map V, which is a valuation, to some idempotent semi-ring T. And if I ever forget to say idempotent, every semi-ring in this talk is idempotent. So I've got a valuation V. I've got a map W up to S here. S has a differential, and this is also an idempotent semi-ring. And I've got a map pi here. So whole structure that I outlined up here, we're supposed to have W composed with D equals D composed with W. So W intertwines the two differentials, and D satisfies tropical Leibniz. The D on S, I should say. Okay, and this triangle is supposed to commute. So if we're interested originally in the valuation V, and you think of this as some extra auxiliary structure that we put on top of V so that we can now talk about differential equations, then we call this a differential enhancement of V. Or sometimes we'll just call it a differential enhancement to refer to the whole package. So I want to think of this as some auxiliary data that enhances evaluation with the extra structure you need to talk about tropical differential equations. And now we can do the same sort of evaluation given F in the differential polynomials over the downstairs semi-ring T, and P in S to the N. I can evaluate F at P and get an element of T. Okay, now we're going to talk about what it means to be a tropical solution. So this is generalizing the notion of tropical solutions that Alex talked about yesterday. So given such a polynomial, the set of tropical solutions to F is going to be the set of all points P in S to the N, such that, well, if F is equal to a sum over terms alpha of, let's say I've got a coefficient A sub alpha times X to the alpha, in multi-index notation. And these X to the alphas are, these are differential monomials. So the solutions to F are going to be all the points P such that when I look at F of P, which means I'm going to look at the sum over alpha of, oops. I didn't want to circle there. A sub alpha, and now I've got to plug P into this differential monomial and then push it down from S to T. So this summation tropically vanishes. So that's to say that if T is totally ordered, then I'm saying the minimum in the summation occurs at least twice. And if T is not totally ordered, then I'm saying this more general bend relations thing that I can delete any one term from this summation without changing the value of the whole thing. So that's what it means to be a solution. Okay, now let's go through tropicalizing again. So given a differential ideal I in the Rit algebra over R, and R is now my general differential ring R, I'm going to choose the downwards road here and apply V to the coefficients and end up in this kind of a Rit algebra over T. And the tropicalization of I is basically the image in there. And given the solution set, I'm going to take the upwards path. I'm going to apply W component-wise to get to S to the N. And the tropicalization of the solution set sits in here. And then proposition is that the tropicalizations of classical solutions, if I think of this as a set, sits inside the set of tropical solutions. Right? So taking a classical solution, a solution to I, and tropicalizing it will give me a solution to this set of tropical equations here. So this is saying basically that the tropicalization of solutions to I are contained in the tropical solutions of the tropicalized system of differential equations. Okay, so that's an easy proposition with this setup. It's good. And the fundamental theorem, well, it's not really a theorem. It's, I'd say, a question at the moment is, when is this an equality? So in the special case of this setup, that was what Grigoriev introduced, thanks to the theorem of Aroca, Gare, and Togani. We know that in that special case of tropical differential equations, we do have an equality here, which is very useful. It means if you can construct a tropical solution, then you can lift it to a classical solution. But in this more general framework, I don't know if we have an equality there or not. So now let's talk about three facts from non-differential tropical and algebraic geometry and how they relate to this setup. So the first fact is the fundamental theorem. All right, well, I've just addressed that, so let's go on to the second fact. The second fact is that varieties are functors, and so are tropical varieties. I'll explain what I mean by this in a minute. Oh yeah, here, I've got my space ready to explain it right here. So given an ordinary ideal inside a polynomial ring over field little k, I can look at a field extension big K, and I can look at the variety associated with I, which sits in little k to the n. But I can also think of this as, this ideal as defining a functor which sends this field extension, big K over little k, to the set of points of the ideal where I extend scalars to my big field. Now, you can get this thing by looking at homomorphisms from, this is very, very basic idea from scheme theory that everybody here knows, I'm sure. We can take the quotient object here and look at homomorphisms of K algebras from this thing into big K. And so this object here, this ring, or this K algebra, represents the functor of solutions to this system of equations over field extensions. And obviously you can more generally talk about field extensions over little k algebras that aren't necessarily field extensions. So it turns out that we have the same picture for tropical varieties. I can tropicalize this ideal I and get a system of tropical polynomial equations inside the semi-ring of tropical polynomials. And then I can look at tropical polynomials modulo, well, there's a certain equivalence relation built out of the things in here. I'm just going to write this without taking the time to explain this as the bend relations of all of the polynomials f in trop of I. So this is a certain congruence that we build, which enforces this relation that all of these f's have to tropically vanish. They have to satisfy that you delete any one term without changing the value of the thing. So f is equivalent to all of its single term deletions. And this thing here, if I look at homomorphisms from this, into T, this gives me the tropicalization of the variety of this ideal I. And now, if you want to think about a functor, you can replace this T with some other semi-ring. Okay, so that's fact number 2. And the third fact is this well-known theorem that goes back to Sam Payne, which is known as the inverse limit theorem. So given a scheme X with an affine embedding, I can produce the tropicalization, which will sit inside T to the n. And given a different affine embedding, I can produce a different tropicalization. And if I have a monomial morphism of affine spaces, then I get a morphism of, I get an induced morphism of tropicalizations. And Payne's theorem says if you take the Berkovich analytification of X, well, very elementary construction shows that this admits a morphism, it admits a continuous map to each tropicalization. And these maps are all compatible with these changes of embedding. So you get an induced map into the limit over the category of all affine embeddings of the tropicalizations. And Payne's theorem says that this map is a homeomorphism. So X, the analytification maps surjectively to each tropicalization, and it turns into a homeomorphism when you take the inverse limit of all the tropicalizations. So each tropicalization is thought of as a finite approximation to the analytification. And just to remind, if not everybody in the audience is familiar with this, when X is an affine scheme spec A, then the analytification of X is just all the valuations on A that extend the given valuation on the ground field, little k. Okay, so let's think about analogs of these three things for tropical differential equations. Fundamental theorem, well, we don't know yet. That's a question that Stefano and I would like to take a look at soon. The view of solutions as being given by functors, actually, we do have a tropical differential equation analog of that. And the inverse limit theorem, if I have time, I'll get to this. We do have a differential version of the inverse limit theorem. So the only one left of these three is the fundamental theorem, which obviously we know in the special case that was proven by Aroca, Gare, and Togani. So let me talk about number 2, which will then hopefully lead me to number 3 in the last 7 minutes or so here. Given a differential R algebra A, and let's suppose that R has one of these differential enhancements. So R has a valuation here, and it's got this W thing, which is refining that. This is a differential enhancement of this valuation V. I can look at affine embeddings of spec A into an affine space if we're in the non-differential world. And in the differential world, the analog of affine embeddings is just purely in terms of algebra, it's presentations of A, meaning I've got a Rit algebra, and I've got a surjective homomorphism from this Rit algebra onto A, so surjective homomorphism alpha. So A is isomorphic to R, this Rit algebra, modulo the differential ideal, which is the kernel of alpha. Okay, so I can think of this differential algebra A relative to this presentation, this kind of differential affine embedding. It is given by this system of differential equations in these particular coordinates. So if we tropicalize the equations, then I have, well, using this picture up here, I can do my tropicalization procedure, and I get the tropicalization of the kernel of alpha is some sort of a subset inside here. In fact, this is an example of something called a tropical ideal, which turns out to have a lot of beautiful structure that's been studied by Diane McLagan and Felipe Rincon. I highly recommend their papers. So we have this thing in here. That's the tropicalizing the equations. But now let's think about what's going on with the upstairs part. So upstairs, the guess is you might try to form a Rit algebra with coefficients in the S, and then try to extend the differential on S to a differential on the whole thing. And this gets a little bit interesting. This is one of the twists that I referred to in the abstract. Well, so what is the definition of the differential here? Well, first of all, we want that if I have xi and xj and I and j are not equal to each other, then we have the ordinary Leibniz rule. So this is dxi times xj plus xi dxj. So ordinary Leibniz. And I have a kind of ordinary Leibniz with respect to coefficients coming from S here. So this S is in my coefficient semi-ring. So in this case, I should get ds times xu, this is multi-index notation again, plus S times d of xu, whatever that works out to in terms of this first rule, unless you have a repeated power, and then we come to the final rule that we need here, which is what happens when I have some power of x sub I. This is the one interesting one. Then I'm going to write this as W, so that's the W that was part of this differential enhancement structure on R. That's this W here. W of m times xi to the m minus 1 times the derivative of xi. Right, so it's this kind of tropical power law differentiation rule. Okay, now I realize I'm running low on time, but I'm near the end here. So these pairs where I have a differential semi-ring, where we have this tropical Leibniz rule up top, and an ordinary semi-ring down below and a homomorphism. These things I call pairs. These seem to be the thing that we want to use to construct tropicalizations as objects. So what I'm going to do is look at these tropical Rit algebras like this, and they map pi from S to T. Now I extend to the Rit algebras by applying pi to the coefficients. And then down here, I want to take a quotient by these bend relations of my system of equations, which was the tropicalization of the kernel of alpha Alpha was this map here. So I'm going to tropicalize, kernel of alpha is the equations in some particular coordinates defining this differential algebra A. And I'm taking the kernel of that and I'm tropicalizing that system of differential equations to get a system of tropical differential equations in here. Scroll down again. So I take the bend relations of the tropicalization of the kernel of alpha. Okay, this is good, but what do I do up here? This thing is actually too big. And I need to make it a little, I need to take a quotient of this because there's too much wiggle room up here at the moment. And it took Stefano and me a long time to understand this. What we need to do is something called taking the reduction. And the reduction just means I take this differential semiring and I look at the maximal quotient of this differential semiring that still sits over this semiring. So this is the maximal quotient in the category of differential semirings over this non-differential semiring down here. So this thing here, this pair of a differential semiring over a non-differential semiring is what I'm going to call the tropicalization of, tropicalization with respect to this presentation alpha of A. And now, let me state a proposition. I realize I'm just about out of time. Solutions to a system of tropical differential equations in, let's say I've got some pair S prime over T prime, which is an extension of S over T, correspond to homomorphisms of pairs from this thing that I just defined to S prime over T prime. And it should be compatible with the structure maps from S over T. So just a bit of perspective here. Affine schemes are anti-equivalent to commutative rings. Tropical affine schemes, this is coming from the scheme theoretic view of tropical geometry, they live inside, or they're anti-equivalent to a subcategory. I'll put an op there. They're anti-equivalent to a subcategory of idempotent semirings. And this is part of the story of why tropical ideals are very special among all ideals inside these tropical polynomial semirings. And what I want to argue here is that tropical differential schemes, in the very analogous way, live inside this category of, it should be reduced pairs. S over T. So S is a differential semiring satisfying the tropical Leibniz rule, and T is a non-differential semiring. So I think somebody just said something in the chat. Yes, affine. Thank you, Martin. And in my last 30 seconds here, I can state the inverse limit theorem. So suppose we have R with a valuation to T in this very abstract setting, and a differential enhancement of that. And then I've got some differential algebra A, which is a differential R algebra. I'm going to define the differential analytification of A to be the set of all differential enhancements on A, so A maps to S and to T by this WV structure, that extend the given one on R. So I'm looking at all the ways of extending the differential enhancement on R, the valuation and this extra differential piece. I'm extending that from R to A. So this is my differential analog of the Berkovich analytification. And the inverse limit theorem that Stefano and I have been working on says this analytification is the inverse limit over all these differential presentations of A of the solution set to the tropicalization of the corresponding system of differential equations. Okay, that's me done. Thank you very much, and hopefully I have left enough time for a couple of questions.